Inside this little drive there are no moving parts at all, just electrons sitting in tiny traps. Let us open up an SSD and see how it really works. For decades, storage meant a hard drive, a metal disk spinning thousands of times a minute, with a tiny head flying just above it, reaching for your data. It works, but it is slow, and one bump can wreck it. A solid-state drive throws all of that away. No disk, no head, nothing that moves. Just chips. And that one change makes it faster, tougher, and silent. It also sips far less power, which is why every modern lap ships with one. This is not new technology. Flash memory was invented back in the 1980s in Japan. The first flash drives were tiny and wildly expensive. It took until around 2007 for them to reach laptops. Then prices fell. A clever trick called 3D stacking arrived, and a faster language called NVMe took over. 40 years, from lab to everywhere. So how does a chip remember anything? At the bottom of it all is one idea. A single bit is just a tiny packet of electric charge trapped inside a cell. If the charge is there, that is a 1. If it is gone, a 0. And here is the magic. When you cut the power, the charge stays put. That is why your files are still there tomorrow. We call that non-volatile. Let us zoom into one cell. It is a special transistor with an extra layer in the middle, completely wrapped in insulation. We call it the floating gate. To store a bit, the drive hits it with a high voltage, which forces electrons to jump through a thin barrier and onto that gate. Once they are there, they are stuck with nowhere to go. The charge is trapped. Reading the cell is the clever part. We never count the electrons directly. Instead, that trapped charge changes the voltage needed to switch the cell on. An empty cell flips easily. A charged one needs more push. So the drive applies a reference voltage in between and just checks which side the cell falls on, 1 or 0. That is a read. Now, the simplest design uses just 2 levels of charge, empty or full. 2 levels, 1 bit. We call it single-level cell or SLC, because the 2 states are so far apart is incredibly fast, and it lasts a very long time. The catch: it is expensive because each cell only holds a single bit. So engineers asked a bold question. What if we use the same cell but store more? Instead of 2 levels, use 4, and you get 2 bits. That is, MLC use 8 levels for 3 bits, TL 16 levels for 4 bits, QLC same cell, more data. But look closely. Every time we add a bit, the levels get packed tighter, and the room for error shrinks. And that is the great trade-off of every drive. More bits per cell means a cheaper, bigger SSD, but it also means slower writes and a shorter life. SLC can be rewritten around 100,000 times. QLC maybe 1,000. So the flash in a cheap 2 terabyte drive is the same idea as the flash in a pricey one, just packed harder. That single trade-off is the whole reason drives keep getting bigger and cheaper, year after year. These cells are not used one at a time. They are grouped. A row of cells forms a page, and that is the smallest chunk you can write to. Many pages form a block. And here is the quirk that shapes everything. You can write a single page, but you cannot erase one. To erase, you have to wipe an entire block at once. This causes a strange problem. Say a block is half full of old, dead data. To reuse it, the drive first copies every still good page out to a fresh block. Only then can it erase the old one. So a small write from you can trigger a much larger shuffle behind the scenes. Engineers call this write amplification, and taming it is a real art. Managing all of this is a tiny computer on the drive, called the controller. It is the real brain. It keeps a map from your file locations to the actual chips. It spreads writes evenly, so no single block wears out first. It fixes bit errors on the fly, runs cleanup in the background, and hides a little spare capacity for emergencies. A weak controller can ruin great flash. 2 drives with the very same chips can perform worlds apart, just because of the brain in charge. For years, drives got bigger by shrinking the cells, but cells can only get so small before they start leaking charge into each other. So makers turned the cells on their side and began stacking them upward like floors in a tower. The first stacks were a few dozen layers. Today, the best drives stack more than 200. That is how we got huge, cheap storage. The same flat footprint now holds many times more data than before. This explains something you may have seen. Copy a big folder and the speed is blazing at first, then suddenly drops. The drive treats part of itself as fast SSD, a turbo cache. When that cache fills, you fall back to the slower real speed. And a small chip of DRAM on the drive holds the address map, so lookups stay quick. Cheaper drives skip it and borrow a little of your computer's memory instead. Now, how does the drive talk to your computer? The old way is SATA, a connection from the hard drive era. It has one lane and lines up only a few requests at a time. NVMe is the modern way. It plugs straight into the fast PCIe lanes and opens thousands of queues at once. Same flash, but NVMe can be 10 times quicker, simply because it stops waiting in line. That flash comes in a few shapes. The flat 2.5-inch drive that replaces a laptop hard drive, the slim stick called M.2 that lies right on the motherboard, and bigger cards for servers. And the speed keeps climbing. Each new generation of PCIe roughly doubles the limit. Gen 3 gave about 3.5 gigabytes a second, Gen 4 around 7, Gen 5 up to 14. Just remember, an M.2 slot can be wired for either SATA or NVMe, so always check the spec before you buy. So how do you actually choose? A few things really matter. For speed, get NVMe and save SATA for old machines. For the flash, TLC is the sweet spot. Pick QLC only for cheap bulk storage. For heavy use, look for a drive with its own DRAM. Check the endurance rating, the terabytes written. And buy more capacity than you need, because bigger drives are faster and last longer. Finally, match the PCIe generation to your motherboard, since a Gen 5 drive in an older slot will simply run slower. And that is the whole journey. Electrons trapped in a cell, grouped into pages and blocks, packed tighter to go cheaper, managed by a clever controller, stacked into towers, and delivered over NVMe. Next time a file saves in an instant, you will know exactly what happened inside. Thanks for watching.